Alright, in this video we're going to talk about the probability rules. That's section 9.2 in your text. And we will begin with determining the probability of event A or B for mutually exclusive events. Okay, so that's the first thing we'll discuss. Okay, the event A or B is one event consisting of the union of the outcomes in events A and B. So the union in this case, we're just going to be basically joining the two events together, events A and B. So it's just going to be a combination of the two. Like in this example here. Here we're going to list all the outcomes that belong to event A or B. So in part A we got A, which has these elements 1 and 3, and B has these elements 4 and 6. So here A is the event of getting a 1 or 3, and B is the event of getting a 4 or 6. So the event A or B is the event of getting a 1, a 3, a 4, or a 6. So we're just combining the two together. So A or B would be this. The elements 1, 3, 4, and 6. Okay. Now, for part B, we got A, which has 1 and 3, and B, which has 3 and 6. So here, the event, A is the event of getting a 1 or 3, and B is the event of getting a 3 or 6. So, the event A or B is the event of getting a 1, a 3, or 6. So, A or B would be this set, 1, 3, and 6, with those elements. Okay. Now, an elementary mathematics student should understand and use appropriate terminology to describe complementary and mutually exclusive events. Now here's the definition of what mutually exclusive events are. A and B are mutually exclusive events when events A and B cannot possibly occur at the same time. In other words, they do not have any common outcomes. So A has nothing in common with B. No common outcomes. Alright, now the next definition is this. If we know in advance that event A and event B are mutually exclusive, then we could find the probability of event A or B in terms of the probability of A and the probability of B. So here's that definition here. If A and B are mutually exclusive events, then the probability of A or B will be equal to the sum of the probability of event A and the probability of event B. Okay. So in this example here that I'm going to give to you, the following data are based on a report by the CDC from the National Hospital Ambulatory Medical Care Survey for outpatient department visits. So here, what is the likelihood that a patient visited the outpatient department because of an acute problem or for preventative care? And interpret your results from part A. So here's the table that they're giving you here, the reason and the percent, and here they're giving that to you as a decimal. So to answer part A, we're going to let A represent the event that a patient visited the outpatient department because of an acute problem, and let B represent the event that a patient visited the outpatient department for preventive care. Now, as you can see here, these events are mutually exclusive because visits for acute problems are unexpected emergencies, whereas visits for preventive care are scheduled. Okay, so those two have nothing in common. And since they're mutually exclusive, we can use that formula, probability of A or B equaling to the probability of A plus the probability of B. So in this case here, 0.36 represents the probability that a patient visited the outpatient department because of an acute problem. That was 0.36, as you can see here. And the probability of B was the probability that a patient visited the outpatient department for preventive care. So preventive care was 0.18. So add 0.36 to the 0.18, you'll get 0.54. So answering part A, where the likelihood that a patient visited the outpatient department because of an acute problem or for preventive care was 0.54. Okay, now there's the interpretation of that. And now part B, this means we should expect 54 out of every 100 patients visiting the outpatient department would be seen either for an acute problem or for preventive care. Okay. Now take a look at problem number 1. Now this is from your text on page 521. It says here, consider the events A, which is 1, 2, and 6, and B, which is 3 and 5, and the sample space, which is, of course, 1, 2, 3, 4, 5, 6. Now it says here, make a Venn diagram for these sets. Okay. Now, if you're not familiar with what a Venn diagram is, it looks like this. It's just a rectangular box containing circles. And those circles are going to be the sets with those elements that are in that particular set. So for A, here's a circle here. I'm going to label this as A. Now A has the elements 1, 2, and 6, so I'm just going to put those elements in, 1, 2, and 6. Now B has A and B have nothing in common, as you can see there. So the circle, I'll just draw another circle that doesn't intersect. And I'll call that B. And B has the elements 3 and 5. Now, we got 1, 2, and 6, and then 3 and 5. But 4 is not going to be an A or B. So I'm going to put 4 somewhere out here to show that the number 4 is not in set A or in set B. So that is what a Venn diagram looks like. Now part B says to explain how the Venn diagram for events A and B would reveal A and B are mutually exclusive. Well, as you can see here, A and B have nothing in common. Okay, so here the Venn diagram, I'm just writing out the explanation. The Venn diagram shows that A and B have nothing in common. Okay. Those two events have nothing in common at all. Okay. So that's how we explain problem number 1 here. And this is how you would create a Venn diagram for those two sets, A and B. And also the sample space. Okay. Take a look at problem number 5, also on page 521. We're just going to focus on parts A and B for now. The others we'll look at throughout this particular video as well. The Venn diagram represents events A and B for a sample space S with equally likely outcomes. And later on I'm going to explain what that phrase, equally likely outcomes, mean. So this is what the sample space is, and here's set A and B. And then we want to answer these questions. What is the probability that event A will occur? So I'm going to write this as probability P with the A in the parentheses for the probability of event A. Now this circle right here represents A. And I'm going to count up how many dots there are in A. In this case, there are 1, 2, 3, 4, 5, and 6. So your 6 will be your numerator. Your denominator will be the total number of dots that are in the entire sample space. So here we got 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. That's your denominator. So the probability of event A would be 6 over 15. Now if they want this in simplest form, we can divide the numerator and the denominator by 3. That gives us 2/5. And in some cases they may want that as a percent. So if you do 2 divided by 5, you'll get 0.4. But for a percent, you have to multiply it by 100 to get 40%. So the probability that event A will occur would be either one of these 3 forms: 6 over 15, or 2/5 in simplest form, or 40% as a percent. Part B, what is the probability that event B will occur? So the notation would be probability that event B will occur. Well, this circle right here represents event B. We'll count up how many dots there are in B. So no, we got to count these 3, then 4, 5, 6, 7, 8, 9, 10. And there were 15 dots in the entire sample space, so the probability of event B would be 10 over 15. Now if I reduce 10 over 15, this will be 2/3 by dividing the numerator and the denominator by 5. And then if I want to write that as a percent, I'll have to do 2 divided by 3. And then times 100. It's going to give me this decimal value, 66.6666. But I'm going to round this off to one decimal place, so it'll be 66.7%. So this will be approximately 66.7%. Okay. Okay. All right, next we'll look at determining the probability of events A or B in any events. A or B, and it could be any events here. In this example, well, let's say in this situation, suppose an experiment consists of rolling a standard die and then recording the number of dots that appear on the top face. So let A would be the set 2, 4, and B has these elements 2, 3, and 5. So what is the probability of event A or B? Here you can see that events A and B are not mutually exclusive because A and B can occur at the same time by rolling a 2. So we cannot apply this particular formula because it's not mutually exclusive. Okay? So let's take a look at what we already know. We already know the sample space, which is 1, 2, 3, 4, 5, and 6. We know the probability that of event A will be 2 over 6 because there were 2 numbers out of a possible 6. And the probability of event B was 3 over 6 because there are 3 numbers out of a possible 6. All right, next. I'm sorry. Forgot this one. Here we go. A or B is going to be this. 2, 3, 4, and 5. You put the two together, events A and B together. So the probability of event A or B would be 4 out of 6. Now, A and B, if you find the element that's common in both A and B, it will have to be the number 2. So that means the probability of A and B will be 1 out of 6. So to find the probability of event A or B, well, A or B will be 4 6, and that's going to be equal to 5 over 6 minus 1 over 6, which is, of course, 2/3 plus 1/3 minus 1/6. So here, that's going to give us the probability of event A plus the probability of event B minus the probability of event A and B. So here we will work going backwards on this particular problem here to show you another formula for finding the probability of two events A or B if you don't have mutually exclusive events here. So here's our definition. If A and B are any events, then the probability of A or B will be equal to the probability of A plus the probability of B minus the probability of A and B. So you want to check to see if your two events are mutually exclusive. We can use that first formula. If they're not, then we have to use this one. Okay, we're going to apply that to example 20 in your book. An experiment consisting of drawing a card from a standard deck of cards. What is the probability of drawing a spade or an ace? And here you got two events, drawing a spade and drawing an ace. The ace of spades belongs to both events. So those two events are not mutually exclusive. Because drawing a spade, there is the ace of spade in it. Okay. So here there are 13 spades in a deck of cards, so the probability of drawing a spade would be 13 over 52. Okay, and the 52 is the number of cards in a standard deck. And there are 4 aces, so the probability of an ace would be 4 out of 52. Now next, there is one card that is both a spade and an ace. That's the ace of spade. So the probability of drawing a spade and an ace would be 1 out of 52. Okay, so that's the other formula that we have to use for non-mutually exclusive events here. So the probability of drawing a spade would be 13 out of 52, plus the probability of drawing an ace would be 4 over 52, minus the probability of drawing a spade and an ace, which is that ace of spade, 1 over 52. And that's equal to 16 over 52. Now if we convert that to a percent, it'll be approximately 30.8%. Alright, next is an example, well, this is problem number 2 on page 521, dealing with mutually exclusive events. Here we want to consider the events 1, 2, and 6, and B would be 2, 3, and 6. And the sample space consists of S equal 1, 2, 3, 4, 5, and 6. And this is non-mutually exclusive events here. Here I want to make a Venn diagram for these sets. Okay. Now this one we're going to have to do the Venn diagram, and it's going to look different. The reason being is because A and B has a number that's in both, and that's the number 6. So this is how we're going to do this. I'm going to draw one circle here, and I'm going to draw another circle. This time it's going to intersect the other circle. So this is A, and that's B. The number that's in both A and B will have to be the 6. that's going to be placed in that intersection that you see there. And then A has 1, 2, and 6. Well, I got the 6, so I need to put the 1 and the 2 on the outside. And B has 2, 3, and 6. Well, I've already got the 6, so I need to put the 2. Oh, that's a correction right there. 2 and 6 are in both. So I need to put 2 and 6 in here. Now I'm going to have to kind of scrunch that in there. The 2 and the 6. And I can white out that. So it's only got the 1 and then the 2 and the 6. And then B will only have the 3 on the outside. And 2 and 6 are in that intersecting part. And I apologize that this is not clear. So it's just 2 and 6 there. That's your Venn diagram. Next is to explain how the Venn diagram for events A and B would reveal A and B are not mutually exclusive. Well, in this case, that Venn diagram does show that the intersection, which is what this is, based on that Venn diagram, is non-empty. Okay. So that's what problem number 2 is and what that looks like from a Venn diagram perspective. Okay. All right. Here's problem number 5 on page 521. Now this is only part D. That same Venn diagram does represent events A and B for a sample space S with equally likely outcomes. And here I want to find out what is the probability that event A or B will occur. So the probability of event A or B, I'm going to use that formula for non-mutually exclusive because there is an intersection, as you can see here. So I have to use this, the probability of event A plus the probability of event B minus the probability of event A and B occurring. Now back in the part A and B of example 5 in the earlier slide, we found the probability of event A, and I'm going to use 6 over 15. And then plus the probability of event B occurring was 10 over 15. But we need to subtract off the overlap. That's this intersection right here. Probability of event A and B would be this intersection right here, this football looking thing. It has 3 dots in it. So it's 3 out of the total number of dots, which is 15. And if I add 6 and 10, you'll get 16. 16 minus 3 would be 13 out of 15. So in this case here, if I do 13 divided by 15 times 100 and write as a percent to 1 decimal place, it'll be approximately 86.7%. So that represents a probability that event A and B will occur. Alright, next we'll look at determining the probability of event A and B for independent events. So this time it's A and B, and we're going to be dealing with independent events. Here's some definitions that you need to know here. When we say the two events A and B are independent events, we mean that the occurrence of A does not affect the probability that event B will occur. So let's say event A was tossing a fair die, and then the second event was tossing a fair coin. Tossing a fair die has nothing to do, no effect on what I get when I toss a fair coin. That's what independent events are. One has nothing to do with the other. Now, when we say that the two events A and B are dependent events, we mean that the occurrence of A does affect the probability that event B will occur. Okay? Let's look at this example. Determine the probability of drawing an ace from a standard deck of cards. Okay. And then part B is an experiment consists of drawing two cards from a standard deck of cards with replacement. This means we return the first card to the deck before drawing the second card. A is the event that the first card is a 5, and B is the event that the second card is an ace. Explain why event A and event B are independent. Okay, now let's answer part A. Well, okay, I'll get to part C first, but let's answer part A on this particular slide here. The probability of drawing an ace is going to be pretty much 4 over 52. There are 4 aces in a deck of 52 playing cards. Okay? Now, in part B, we're going to assume event A occurred, where a 5 was drawn and then returned to the deck. There are 4 aces in the deck of 52 playing cards, so the probability of drawing an ace is 4 over 52. The occurrence of event A did not affect the probability of drawing an ace. It is still going to be 4 over 52. So you can see that event A and event B are independent. Okay, now, here's part C. An experiment consists of drawing two cards from a standard deck of cards without replacement. This means we do not return the first card to the deck before drawing the second card. A is the event that the first card is a 5, and B is the event that the second card is an ace. Explain why event A and event B are dependent. Okay. So, in this case here, we're going to assume event A occurred. That means a 5 was drawn but not returned to the deck. Excuse me. There are 4 aces in the 51 cards remaining in the deck because we're not returning the 5 to that deck. So the probability of drawing an ace will now be 4 over 51. The occurrence of event A affected the probability of drawing an ace. It changed from 4 over 52 to now 4 over 51. So event A and event B are considered to be dependent events. So those are just a couple of illustrations of what independent events are and what dependent events are. Okay, now here's another definition here. If events A and B are independent events, then the probability that both A and B will occur is the probability of A and B equaling to the probability of A times the probability of event B. So in this example here, an experiment consists of tossing a fair coin 5 times in a row. Which outcome is more likely? This one, which is HT, HHT, or all 5 T's, which is all 5 tails in this case. Now, tossing a fair coin repeatedly involves independent events. For example, the outcome of the first coin toss does not affect the probability of getting tails on the second toss. So on any toss, the probability of heads will be 1/2, and the probability of a tail will be 1/2. So here, we're going to multiply, as you can see here. The probability of the heads, probability of the tails, probability of heads, probability of heads, probability of tails. That's the product of all 5 of those. And you will get 1/2 as a factor 5 times. So if you multiply 1/2 times a half times a half times a half times another half, you'll get 1/32. So the probability for that event will be 1/32. And the probability of getting 5 tails on 5 tosses, again, we're going to multiply, and that probability of a tail will be 1/2. So again, 1/2 as a factor of 5 times will be 1/32. So you can see here the outcomes are going to be equally likely. Equally likely. Take a look at problem number 5C on page 522. The Venn diagram represents events A and B for a sample space with equally likely outcomes. And here I want to find the probability that event A and B will occur. Well, pretty much we don't have to do any math here, because if you look at this part right here, the intersection, which is like a football, that's the probability of event A and B occurring. And there are 3 dots in that intersection, so the probability of A and B occurring would be 3 out of 15. And if I reduce 3/15, that would be like 1/5. And as a percent, if you do 1 divided by 5, multiply that by 100%, you'll get 20%. So in this case here, 20% represents the probability of event A and B occurring. Okay. Now problem number 12 on page 523. Looks like this. You're given the probability of event A will be 0.3, the probability of event B will be 0.5, and A and B are independent events. That's very important. They're independent events. And in this case, I want to compute each probability. The probability of A and B, and the probability of A or B. So let's start with part A. The probability of A and B. So, that formula, if we write that out, it'll be the probability of A times the probability of B. And that's because A and B are independent events. So in this case here, the probability of A was 0.3 times the probability of B, that's 0.5. Multiply 0.3 times 0.5, you're going to get 0.15. So 0.15 represents the probability of event A and B. Now part B, we want the probability of A or B. Now we're going to be using that formula for non-mutually exclusive events here. That's of course the probability of A plus the probability of B, and then we subtract from it the probability of event A and B. Well, the probability of event A was 0.3, that's given to us, plus the probability of event B, that's given to us as 0.5. We're going to subtract from it the probability of A and B, which we found out in part A, that is 0.15. Okay. So if I do 0.3 plus 0.5, that will be 0.8. 0.8 minus 0.15 will end up being 0.65. That's the probability of event A or B. Okay. All right, here's another example. This is problem number 13 on page, it should say 523, not page 13. You're given that the probability of event A is 0.42 and the probability of event B, that's 0.75. Okay. Here we're going to compute each probability. That is this, the probability of event A and B, and then the probability of A or B. Well, just like in problem number 12, probability of A and B is going to be just multiplying these two, the probability of event A times the probability of event B. And we're told that they are, A and B are independent events. So, probability of A would be 0.42 times, that's the times sign, the probability of event B, that's 0.75, if we multiply those two, you'll get to 3 decimal places 0.315. That's the probability of event A and B. Now for the probability of events A or B, probability of A or B, we're going to use the one for non-mutually exclusive events. Probability of A plus the probability of B minus the probability of A and B. Because we know what the probability of event A is, that's 0.42. The probability of event B will be 0.75 minus the probability of A and B, which is what we found out in part A, 0.315. So if I do 0.42 plus 0.75 minus 0.315, that will end up being 0.855. So the probability of A or B would end up being 0.855. Okay. All right, next we'll look at conditional probability and how to do those type of problems here that deal with conditional probability. Okay, here's a definition of what conditional probability is. We're going to let A and B represent two events. The probability that B will occur given that A already occurred is called the conditional probability of B and is denoted as this. The probability of B with a vertical bar and then A, that says the probability of B given A. So here we're dealing with the probability of event B given that A has already occurred. So let's say in this example here, a bag contains 3 blue marbles, 2 green marbles, and 1 yellow marble. An experiment consists of drawing 2 marbles from the bag at one time without replacement. This means we do not replace the first marble after it is drawn. Here I want to determine the probability that A, the second marble, is green, given that the first marble is blue. And in part B, we're going to determine the probability that the second marble is green, given that the first marble is also green. Okay. So we know the first marble is blue. That means 5 marbles remain. Okay. The first marble was taken out. It was blue. That means there were 6 marbles total. That means there are 5 left, which means 2 blue marbles, 2 green marbles, and 1 yellow marble. Now the probability that the second marble is green will have to be 2/5. So the probability of a green marble being drawn, given that the blue marble was drawn, is 2/5. Now in part B, the first marble was green. That means that 5 marbles remain. This time 3 blue marbles. This time instead of 2, it's only going to be 1 green marble and 1 yellow marble. So the second marble is green. There's only 1 green marble left out of 5, so it'll be 1/5. So the probability that a green drawn a green marble, given that another green marble was drawn, was 1/5. Okay. Now we're revisiting problem number 5, E, F, and G on page 522. Now, it says here, here we got the Venn diagram again for events A and B, sample spaces S, equally likely outcomes again. What's the probability that event A will occur given that event B has occurred? Okay. Now, in this case, I'll just do E here. I'll just say here the probability of event A occurring B, given that B has already happened. Okay. Now B has already happened, so we're just focusing on this circle right here for event B. And we need to count up how many dots there are. So in this case here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That denominator is 10. So out of these 10 marbles, or out of these 10 dots, what will be the probability of event A? These 3 are also in A, so that means that 3 would go in the numerator, so it'll be 3 out of 10, or exactly 30%. When you do 3 divided by 10 times 100. Okay. And I need to give you a little bit of hint about conditional probability. What the conditional probability does, it reduces your sample space. And I'm going to be doing another problem that is related to conditional probability, because that just reduces the sample space, because instead of the whole 15 that is in the sample space, we're only going to be focusing on, in this case, 10, because event B has like 10 dots in that circle. So we'll just focus on that. And now part F. What is the probability that event B will occur given that A has already occurred? Okay, so here, we're only going to focus on event A. So here's A right here. So this is going to be the probability of event B given that A has occurred. Now, how many dots are there in the circle for A? Well, in this case, there's 6. And out of those 6, what would be the probability of event B? Well, these 3 dots are in event B as well. So this will be 3 over 6. Now, if you do 3 divided by 6 times 100, this will be 50%. So The probability of event B occurring given that A has already occurred would be 50%. Now part G, what is the probability that event B will occur given that event A did not occur? That should be event A. Now the way I'm going to write that notation would be like the probability of event B, given that I'm going to use this mark for not A. So that means we're excluding everything in A, including these 3 dots. So what's left in B would be 1, 2, 3, 4, 5, 6, 7. Now if we exclude these, how many dots are in the sample space that are left? That's 1, 2, 3, 4, 5, 6, 7, 8, 9. We'll be left with just what's left in exclusively B and those 2 dots that are on the outside. That's a total of 9. And out of those 9, event B will occur only 7 out of 9. Now if I write that as a percent to the nearest tenth, would be 77.8%. So the probability of event B given that A has not occurred would be 77.8%. Okay. All right. This is only part 1 of this section 9.2. Now, there is a part 2 for this section. I will have that available for you on Blackboard for you to view as well. So, make sure to be on the lookout for part 2 of section 9.1. We'll continue this particular section on another video.